Well, one second. Yeah, we came together as a group because we had a similar vision about having the PV panel interact with its environment. And basically from that, we originated to a problem statement, which actually tackles the problem of overheating solar panels in warm countries. And from that, we derived to some criteria that we want to actually see how much energy output we can produce. And therefore, we didn't want it to use any additional energy just to see how far we can go with this. And as a reference spot to get a general idea about the conditions and some data and some calculations, we picked South India as a reference. And that's where we started off with for our research. So we dove into passive cooling methods to see which techniques can be applied onto a facade and which we can use in our module, and to see how we can increase everything. So optimization, how we can get the most radiation, get the best wind flow, all to generate that best amount of output. And from that research, we basically derived into three basic concepts. One is tackling the wind component. Then you have to think about increasing the velocity, the pressure, and redirecting the wind in order to increase convection rate. One is actually a radiation component, so remove self-shading, different sizes in geometry, in placement, in order to gain as much irradiation as possible. And one is actually the water. We want to use water as a heat exchange medium, and therefore we want to capture the water at rainfall that's falling into warm climates, since it's pretty scarce. And we first thought about storing it in an external water body, but we wanted to solve it inside the facade itself. So we actually came up with ceramics, and the hydroscopic character of ceramics actually allowed us to do that. So first off the wind, we had no idea how to tackle this. So we just started off sketching, discussing, and making modules. And by using a smoke machine, we can actually visualize the airflow. And from that trial and error, we used a CFD simulation for our final result to really simulate it on a one-on-one scale and see how the wind actually flows in real time. For the radiation, we actually parameterized everything, so we can alter the location, the sizes, the facade shapes, and orientation, as well as the aesthetics. And for the water was actually another challenge to saturate the whole facade. So each element of ceramic, we want to water it and make sure it's saturated. So water management was also a big thing. And now we know what we're gonna do. We didn't know how yet. We didn't have a design. So we just said, go ahead, we make a lot of designs and we just rank them from best to worst. And just from that point, we started off having our final design.
So we wanted to explore water absorption through the material. Our literature research actually shows that ceramic has a potential to create evaporation cooling using different binders like charcoal or sawdust to create more porosity in the pieces. However, how to produce such an element was a mystery for us. We explored from 3D printing to hand molding every possible process and geometry. So to understand the material properties, the production process, and the industry of ceramics, we actually had to take a step back. And thanks to Christine Jetten, we were able to explore the world of ceramics and transform from an idea to a reality our project. As a natural effect, clay released moistures out of the mold, creating a shrinking process. We wanted to use the same principle, mixing it with different binders to create more porosity in the material. Taking in consideration that we actually had solid clay and liquid clay, we had to find the perfect material for us. However, despite the fact that liquid clay is used for create complex geometries, for us, it was actually not an option due to the fact that the density between the liquid and the binders is different. On the other hand, solid clay, which is used for more simple geometries, was the best option for us because it was giving us a more homogeneous mixture in the molding process. So basically, our key for the experimentation was to find the balance between the production process and the material. Using as a base three main materials, we basically use chamois, powder clay, and sawdust to find the perfect binder and the perfect proportion to find porosity in ceramics. The way to achieve that, we actually run an absorption test, and we create 6 different tiles of ceramics. 3 of them were baked at 900 degrees, and 3 of them were baked actually at higher temperature From this experimentation, we found two things. The first one is that lower temperature in the killing process actually produce more porosity in ceramics. And the second one is that chamot, which is a reused powder of ceramics, increase the porosity ratio. We actually didn't expect that. So we had our magic mixture. During the building weeks, we've just followed the process of preparing the material, finding the perfection ratio between the binders, mixing the binders with water, and creating and casting the 16 ceramic pieces. For the molding process, we tried to follow the traditional method using actually plaster molds, but due to the fact that we didn't have enough time to produce it, we have to, on the way, produce our own methodology using foam to create more ceramics in lower time.
So from that, we finally had our final geometry, which was based upon having multiple sections and put them together to function as one big geometry. Only when we made the material, there was one hiccup. The material couldn't hold any tension. So our original design was based upon clippers and then hinging it to the construction, but that couldn't work since it would break. So the site system in the Bucky Lab building weeks had to change on a short term, so there could be a lot of increase there. But we were able to build a prototype and test the airflow from the outside wind pressure and from the chimney effect, and as well as the water. And what can be increased is like we have two sets of design right now for the section, and it can be more different designs for the section, making it work even better and even smoother. Like the water can be more saturated along all the panels. As well as the grasshopper script worked, and we were able to make different applications for different buildings. So this was our project, and thanks very much to Christine Jetten, and we are very proud of our project.
Thank you very much, Jens and Juan. You guys have 10 seconds left even. Super quick. All right, thank you very much.